Well, since the last time you saw this control panel, I made an attempt at the wiring and it did not go well. This is a tangled mess. I'm not happy with it, so we're going to redo it today. Welcome back to Cloud42. I'm James. If you remember, this is the control panel for my surface grinder automation project. And I know some of you remember because you've been asking me about it. And here it is. We're getting back on it. This control panel, the last time you saw it, was completed with the front panel. All the controls were mounted and I had it ready to wire up and start actually using it on the grinder. And I've done a couple of things since then. The first thing I did is I created a new base for it. You'll remember this base that is intended to mount on the grinder. The control panel mounts onto this, and then it's got this nice little grommet for the cables to go through to the machinery on the rest of the machine. But I'm going to be going back and forth between the grinder and a desktop workstation where I'm going to be doing most of the software development, and I need this thing to be able to sit on the desk. And this thing will not sit on the desk. So I designed an alternate base for it, and this base just sits on a flat surface, hooks into exactly the same screw holes so that I have a nice stand to put it on the desk. I have some ports on the back to route the cables in and out, and my plan was just to connect all the cables to this. I've got some nice places here for strain relief, and then just route it out through one of these holes, and then when I put it on the grinder, route those same cables out through the grommet. I was not planning on putting connectors on this panel itself. And I didn't really have a plan yet for the total wiring solution, so I figured I'll just go ahead and hook up the wires I have. We'll hook them in here, we'll let them dangle out the back, and I will deal with it later. And what I've discovered is I can't do that. This is just way too frustrating. These things are always draped over the front of a desk or over the back of the desk or hanging on something, or routing them in and out of the grommets is frustrating. I can't do this. We're going to have to get some proper connectors. We're going to have to do some proper cables, and that's what we're going to do today. Let me cut some zip ties off here and show you the abomination that I have created. Start with the MPG dial. That has got 6 wires on it, and it needs to connect to a 9-pin connector at the microcontroller. So I just bought a 9-pin cable with open leads on the end and connected that in. So there's one cable that has to go back to the microcontroller. And that just connects here with 6 screw terminals. So that's one cable. Get that one out of the way. Second, we've got the adapter here for the display, and that has 2 connections to it. It has a serial connector, and that is just an RJ45, like an Ethernet cable. So there's cable number 2. And it also requires power. The smaller 4D systems displays can run just on power over the RJ45, but the larger ones like this one require 24 volt power to the adapter board. So there's cable number 3, and I just use a twisted pair of 20 gauge machine tool wire, just because that is what I had on hand, and because the other cable that I was going to use for some of the other connectors is too small of a wire gauge, I thought, to carry the current that was going to be required. So next up, we've got these 2 selector switches, and I've got those wired so they require 3 conductors each. I've set these up as analog inputs. We'll talk about that more in a little bit. The cable that I had on hand that was perfect for that is this 3-conductor servo wire. So I've got that, and that is actually soldered directly on and cannot be disconnected. That's another thing that I find really frustrating, aside from the fact of having the additional wires. Now, I could have run these through a cable with the connections for everything else. I was a little bit concerned about interference, but I think these are going to be low enough impedance, it's not really going to be a problem. But with the cable that I had available to me quickly, I also didn't have enough conductors, so I opted to have these separate. So there's 2 more cables. And then the connections for the switches, for the start and stop and the e-stop switches, are a ground connection and then a conductor for each switch. So each switch just closes that to ground. The stop switch and the e-stop switch are normally closed. The start switch is normally open. And those are screw terminals on everything except for the e-stop switch, which inexplicably comes with its own plug. So those are flying leads, and I just crimped those on. So that's a grand total of what? 1, 2, 3, 4, 5, 6 separate cables connecting this. And that is just, this whole thing was a mess. We are going to start over, and we're going to do this with some proper connectors. I looked around for a while at a bunch of different options, and the connectors I decided to use are these. These are commonly referred to as M12 connectors. These ones happen to be A-coded, which just has to do with the tabs in them that allow, A-coded connectors to connect to each other, and B-coded and D-coded won't. These are 8-pin connectors. You'll remember that I used 4-pin connectors on the proximity sensors and the mechanical switches on the grinder table. Those are really commonly used in industrial applications for sensors, but they make them up to, I think, about 17 connectors, 17 pins in them. These ones have got 8, and I decided to use 2. So this is the female end, this is the male end, and my plan is to put one of each on the control panel so that it's not possible to connect the cables to them improperly, and then put one of each on the control box so that then I can connect from the control panel to the control box with a pair of M12 cables. Terminating little connectors like this is always a pain. You've seen me do it in the past by using PCB mounted ones and actually making a PCB to land the connectors and land all of the wires on. But in this case, I opted to go with pre-terminated. These ones came from Automation Direct, and these ones have 1 meter 24 AWG wires on them. So these are already terminated. They're probably crimped, they're inserted, and then they're potted on the back. So these are securely connected, and I can just worry about the wires. Now, the other thing about these is that I want to connect these to the control panel. So all these wires are going to connect to the various points on here, and then I'm going to have these free hanging connectors. And I would like to be able to simply take the control panel off the grinder and move it over onto this base. Now, if I actually mounted the connectors into the back of the base and into the back of the bottom of the base actually on the grinder, I wouldn't be able to do that because I wouldn't be able to take these out. These are rear mount. The threads are on the back, so the wires have to come through. The nut goes on the inside, so there is no way to take these out easily. So if these are permanently attached, or at least attached in a way I don't want to detach all the time to the control panel, then I can't do that. I can't take these in and out. So what I decided to do is just 3D print and insert. Now, this insert doesn't have a single flat side on it, but I was able to get a nice clean print by printing this with a layer of support material. So it was printed down on the bed like this with support under it. This is ABS glass fiber, same material that I used for all of the other parts of the control panel. And then this is just made so that I can mount all the connectors into it. And then I have a solid panel that I can mount from the inside with 2 screws. So I can make a version of the base that takes this. Oh, what do you know? I have one right here that I prepared earlier. So this will just snap into there. And then I have one over on the grinder that's a version of this that has the same geometry, so the panel can just snap in there with 2 screws. So when I want to take the control panel off the grinder and move it into my development workstation, take out those 2 screws, lift this off, stick it in the back. It'll look an awful lot like this, and I can just pull that out and move it very easily with this still tethered to the control panel, and then the wires can coil neatly inside when I actually install it. Now there is one other wire here, so there are enough conductors here to connect up everything except for the serial port, that RJ45 serial port. So I just put an RJ45 bulkhead pass-through connector just like this one, commonly available all over Amazon, so I can use a little short patch cable from here to here, and then I have an RJ45 connector on the outside. So to connect everything up from the control panel to the machine or to the microcontroller for testing, I just need 3 cables, a Cat5 and the 2 M12s. And of course, the advantage of using these industrial style connectors is I can buy pre-made cables that already have injection molded, overmolded strain relief, and these just connect up nice and securely. They'll stay clean, and they should survive very easily in the dusty environment around the surface grinder. Now, to actually land these wires on the controls, I'm not just going to use the bare wire, I'm going to actually use crimp-on ferrules. And what I've discovered over the years is you can buy big assortments of these things, but if you don't have exactly the right size for the wire you're trying to use, it is just trouble trying to get these things crimped. The other thing that I've discovered is if you don't have a good wire stripper and if you don't have a good crimper, you're going to have problems with these. I've got some cheap Chinese crimpers and they work great, except that sometimes the ferrules just fall off after crimping them on. So I splurged and I went out and I bought a nice pair of crimpers. These are the N style, and these do a beautiful job of crimping the wire. So strip it off. Put in the correct size ferrule. Through the crimp cycle, and that will never come off. You might also remember that I invited people to pause the video and look for typos in my labels, and sure enough, somebody got in the comments, and yes, there was a typo there. There was a lot of speculation that I might have been trolling, but alas, that is not the case. It was actually a genuine mistake. So I have printed a new one. I have lasered in corrected markings. You can go ahead and pause the video and check my spelling here, but I think this one is finally correct. And I did one other thing with this new panel, and that is that I created some places to put some terminal strips here. Because of the flying wires coming off of the e-stop switch, I wanted to have some screw terminals to land those on. And because I soldered the wires onto the selector switches here, I wanted to have some place to land those. And so with this, I should be able to do absolutely everything on the new panel just with crimp and screw terminals, and I shouldn't have anything that's attached permanently that can't be disconnected if I want to change something or if I just need to move things around. So let me get all the controls moved from this one over to this one, and then we can get started wiring. Okay, I'm liking the look of this. I've got everything transferred over. Got all the controls here. Everything is attached in the right place, and we're ready to do the wiring. I've already taken the wires from the selector switches and landed those on the screw terminal strip. And I've taken the controls here from the e-stop switch, and I've landed those on the control strip, on the terminal strip there as well. So now we just need to bring in the wires from the connector panel and land those. Now this is going to sit on the machine right about here, and when it's on the desk, it's going to sit right about here. So I want these wires to come in, make a nice little graceful loop, and then land right here on these strain relief locations that I've got. So that looks about right to me. Let me make sure I've got the same length on all these wires. And let me throw in a zip tie if I can figure out what I did with them. Make sure that's going to be about right. And we'll cinch that down. Okay, that's good. Now we need to figure out which wires are going where. So I've got a pin out here that I've worked out, cable A, cable B. So this is cable A, which is male on the control panel end. This is cable B. Cable B, I've got a zip tie on the end so I can tell which one that is. Cable B is for the controls on this side. Cable A is for the HMI power here and the encoder. So this one will come around this way. And then I also need the wires that are going to go here, and that's off of cable B, gray, pink, blue, and red. Okay, that's one wire terminated. Let me do the rest of these and I'll bring you back when it's done. Well, I spent about an hour wiring this and I am so much happier with the result. Compared to what I had in here before, this is nice and neat and tidy. It feels like something I can live with. It feels like something I can work on. And there is something about nice, neatly routed wires that just makes me feel good about the project. So I am not at all upset about the hour or so that I spent wiring this. Just spent some time with my crimper and my wire strippers and just enjoyed myself. So let's take a look at what's in here. First thing here is the e-stop switch, and of course it has a connector with flying leads, and I've just brought those down to a terminal block where it was really easy to attach to these wires with, crimp ferrules under the screw terminals. Same for the start and stop switches. Now, all of these switch to ground, so they share a common ground, and that's what this white wire is. And I made a specific choice to take the ground wire coming in, take it to this switch first, then this one, then loop through to the e-stop switch. The e-stop switch is wired so that it is normally closed. During operation, when it is not pressed, this switch is closed. So in order for the microcontroller to see that it's closed, I have to have continuity of this ground all the way through the loop, all the way to this switch. So if there's a break someplace that might prevent one of these other buttons from working, that will look to the microcontroller like the e-stop has been triggered. And that is a safety measure just to make sure that if there is a loose ground wire in here, that will actually trigger. Now, the stop button is also wired normally closed for exactly the same reason, so it will also look potentially like the stop button has been pressed, and the start button is wired normally open. So what that means is if there's a broken wire, the stop will get triggered, the e-stop will get triggered, and it will not be possible to actually start the grinder. So I made those choices to make sure that this would fail in the safest way possible. The actual MPG encoder is just 6 wires, and I just brought those around, crimped ferrules on them, and landed those on the screws. Now, these screws don't actually have the little square clamping washers on them, so the single prong ferrule is just captured under the screw. It's not ideal, but it will work. I could have put fork terminals on these, but they're bigger and bulkier, and in any case, if any of these wires do come loose, the worst that can happen is we just won't see a quadrature signal and it won't be possible to move the grinder. Again, it fails safely. Then we've got 2 conductors that come over to provide auxiliary power down to the touchscreen. And then the last thing here are these 2 selector switches. And these are the selector switches on the front for moving the axes. Select Y, select the resolution, and then move it with the MPG. Now, I had originally decided to wire those up as digital inputs, so they were going to require quite a few more wires. After talking to the guys at Technic about this specifically, they suggested making those analog. So that's what I ended up doing. We'll talk about a little bit about that in a minute. But because these are solder back switches and I have the wires actually soldered to them, I wanted to have a terminal strip to land those wires on as well, just like with this connector, so I didn't end up with crimps or permanently attached wires that couldn't be disconnected. So this way I can cut these zip ties, the whole wiring harness can come out, and I can do maintenance and parts replacement in here, no problem. I don't have anything in here that is permanently attached, and that makes the whole situation a lot easier to deal with, especially given that the connector panel itself also detaches from whatever enclosure this is in. So this should be as easy to work with as I could possibly make it. The last thing I need is an RJ45 connection for the serial port here for the display up to this RJ45 bulkhead, and then this should be ready to install in an enclosure. And that's that. You can see the connector panel here in the back. It's probably not in focus. And that just protrudes through, and it's exactly the same thing when I install this over on the surface grinder, only instead of protruding through the back, it protrudes through the bottom. But with this, I can put the screws in the sides. Don't have to, but then I have a nice, neat little package that I can just sit on the desk, and I can connect my cables up to the back, and I have a platform for software development. If you saw the previous videos on this, you know that there are two selector switches here, and these are to select the axis and the resolution for the MPG. And each one of these switches has 4 positions, and these are just 4 position selector switches. So I could use 5 wires per switch, 1 ground and then 4 outputs, or maybe 3 outputs, and I would just assume if there was no connection that it was in the 4th position. But that's going to take between the 2 of these at least 7 wires and 6 inputs on the microcontroller. And I don't have that many inputs. There are ways to expand and get that. You can get expansion boards that have more inputs. But when I was talking to the guys at Technic, they said that what they usually suggest is just to use an analog input for a multi-position selector switch, and to just set the selector switch up with a resistor divider so that it outputs different voltages at each position. So that is exactly what I decided to do. Now there is a little bit of complexity to the circuit, and that's because the power supply that I have to work with is 24 volts. But the analog inputs on the ClearCore take a voltage between 0 and 10 volts, just because this is customary in industrial applications. This is how you'll see the speed potentiometer wired up on a VFD, for example. So I need to set up a voltage divider with resistors that will give me 4 distinct voltages in the range of 0 to 10 volts. And ideally, I would like those to be 0, 3.3 volts, 6.6 volts, and 10 volts. So evenly spaced throughout that 0 to 10 volt range. So that means I need a resistor divider with resistors between the poles of the switch and a resistor from the topmost position up to 24 volts. And I need to figure out what size of resistors I want to use for that. Now, overall, I have to decide how much current I want to flow through this, and that's what sets the impedance of this circuit. If I use very high values for these resistors and have a very, very small amount of current going through this, then I'm providing a high impedance signal to the microcontroller, and that's going to be more susceptible to noise from adjacent wires or EMI in the shop environment than if I have relatively low resistances and more current flowing, which would be a lower impedance source. So I decided I wanted to have 10 milliamps flowing. So if we just take Ohm's law equals IR and then rearrange this to solve for resistance. So E is voltage, electromotive force, that's what E is for. And that's 24 volts over my current, 0.01, that's 10 milliamps. Then solve for R, I need 2400 ohms total. And since I need 3 of one identical value and one other, that works out very conveniently to a 1400 ohm resistor and 3 333 ohm resistors. There's no coincidence here that it's 2400 ohms for 24 volts to get 10 milliamps. That's how it works out. So in this case, if I've got a 330 ohm resistor, that will end up with 10 milliamps flowing through it with 3.3 volts across it, 3.3 volts across this resistor, 3.3 volts across this resistor, and 14 volts across this one. So there's lots of ways to construct this circuit. I could have used a PCB mount switch and actually put all of these resistors and some termination screw terminals on a PCB and mounted that on the back of the switch. I could take actual, physical point-to-point through-hole resistors and wired those between the terminals of the switch. But what I decided to do is just get surface mount resistors, because the 0805 resistors turn out to fit very conveniently between the pins on the back of these small switches. So I just got under a microscope and very carefully soldered these resistors in place. Between pin 1 and pin 2, there's a 330 ohm resistor between 2 and 3, and between 3 and 4. Now, conveniently, this switch then has some additional unused pins, so I could solder my 1400 ohm resistor between pin 4 and what would have been pin 5 if it were a 5-position switch, but that terminal's not connected, so I could just use it as a tie-off point for the resistor, which makes this whole thing very easily constructed on the back of the switch. If I had it to do over again, would I do it the same way? Probably. It's pretty convenient. I mean, it would be really neat to make a PCB for this, but it really isn't necessary for an application like this. Now, I did not have a 1400 ohm resistor in my collection, so I just found 2 resistors in series that came out to a total of 1400 ohms, and that also then reduces the power dissipation because there are 14 volts across this resistor, and I'm using 0805 resistors. I needed to make sure, because 10 milliamps across that whole 14 volts is going to dissipate a fair bit of heat, but by splitting it up between 2 resistors, I can easily stay under the power handling capacity of 2 resistors more easily than 1. The other option, of course, would have been to go with a larger resistor, but that wouldn't have soldered in place as conveniently, and I don't actually have a resistor assortment of anything larger than 0805. And just to be sure, we can actually do the power calculations. In this case, power is current times voltage. So if we take 10 milliamps times 3.3 volts, that's 0.033 watts. And that's well within the power handling capability of the resistors that I chose. And the 2 resistors that I have up here on top, the largest of those is 1000 ohms, which would be 10 volts. And so 10 milliamps through 10 volts is 1/10 of a watt, and that is also within the power handling capacity of the resistor. So we should be good to go with that configuration. For the microcontroller end, I've done essentially the same thing. I created an identical panel, except for I've swapped the gender of these 2 connectors. I've got the female one in the A position and the male one in the B position. So I have a male to female cable. I have 2 of those, and I connect them between the 2, and there's no way to screw it up. Maybe I can find a way to screw it up, but I'm less likely to screw it up this way. Now on this end, this is ultimately going to be mounted into a control box, but I don't have the control box yet. I don't have that on the machine. I'm just getting ready to do the software development on this, so I'm going to have this sitting on a bench. So I went ahead and left all of these wires long, and I just landed them on all of the terminals on the microcontroller. Now, I had originally planned on using a DB9 cable because the encoder has to connect to a DB9 connector here, but that means that I couldn't use these connectors. I would have yet another cable that had to go end to end, and I either have a bunch of DB9 connectors, which I absolutely hate, and you should too, or I would end up with another cable that's attached permanently and can't be detached. So what I did is I just got one of these little adapters, and this is just a DB9 to screw terminal breakout, and that allows me to use these same wires with the same ferrules and just land them on the screws. And then that can be landed on the encoder adapter in the DB9. So nice and simple, and when this is all mounted inside of a control box, this means that once again, we've got screw terminals on everything. Then we've got the same RJ45 to connect this down to the COM port, and this should be ready to run. Now, in preparation to power this up, I did a lot of double checking. I double checked my pinouts, I double checked my wiring, I got a continuity tester and did some continuity testing end to end just to try to make sure that I really didn't screw anything up. We've got 24 volt circuits in here, and we've got 5 volt circuits in here. We've got digital, we've got analog, and I really wanted to make sure that everything was right. So like if I probe here, this should be the e-stop switch, and when I open it, I have continuity. When I press it, it's broken. So that all appears to be working. I did probe out the power lines internally. I probed out all of the encoder lines internally. So I think we're ready to apply power to this for the first time. And we should be able to see with the indicator lights on here, some of the switches moving. We should be able to see the display power up. I honestly haven't programmed it yet, so I have no idea what will appear on it when it gets power, but we can try it. Now I'm going to power this up, and if you can see something that I can't and you're currently screaming at your device telling me not to power it on because I'm going to blow something up, you need to scream louder because I can't hear you. So I'm going to go ahead and do it. I have a power supply here. I will go ahead and connect that to the power input jack. This is a digitally controlled power supply. I've currently got it set to 24 volts, 1 amp maximum current. The output is off. I think I've done everything I need to do. I think I'm ready. Let's just power this thing up and see what happens. Okay. I don't smell anything. I don't see any smoke. And the display's up. It's giving me information. This has not been programmed yet, so I wouldn't expect to see anything else there. Let's take a look at the input LEDs. Now, fortunately, there are input lights on the clear core, so I can see what the inputs are doing. Here's the e-stop. Yep, and when that's out, I get my normally closed condition. This LED right here is on. When I press it, that goes out. The run button should be right here. And I see the LED activity from that. The stop button is normally closed. It's already lit. And when I press it, it goes out. Okay. And then my 2 analog inputs. That makes sense because these are going to be inputting voltages 0, 3.3, 6.6, and 10 volts. And if they're on anything other than 0, the light is lit. And if I turn them all the way to 0, the light goes out. In fact, the light's dimmer on 3.3 than it is on 6.6 than it is on 10. So those appear to be working. And then the last thing is the MPG, and we should be able to see the A and B lights of the encoder down here. And yes, those are flashing, and you can actually see them flashing here. Those parallel onto the digital inputs here, 7 and 6. And I think actually 8 if you're using the index input, but I don't have that. So as I turn this slowly, you can see the quadrature signal flashing on those LEDs. Okay. So I think everything's working. I mean, I actually think everything is working. I gotta say, I'm a little bit surprised. I don't think I've ever had a system this complex. I mean, this isn't that complex, but there's a lot of little wires here. Good job, James. You didn't blow anything up yet. So the next step in this project is going to be software development. And I feel like I've got a pretty good platform here. So I can take this. This can sit on my desk. I'll definitely put the screws in it so that it doesn't fall apart when I'm handling it. So can sit on my desk right next to my development workstation. I can have this sitting nearby, plugged into USB so that I can program it. I think there's a USB port on the display as well that I can connect up. And so then I should be able to sit at my workstation and just iterate on the software and have this all as a development platform. So I don't have to come out and have it actually on the grinder connected to the machine. I may need to dummy up some feedback for the motor so that the software will continue to run. Might also be nice to actually see the output of what the motors are doing, you know, have that sitting on the desk or something. I don't know. We'll see. It just depends on how complex this gets and how much debugging I end up having to do. But for now, I think this is an excellent start. I know a lot of you have been waiting for this project for a long time. I have too. Things have come up and it has just taken me some time, but I am back on it now and we'll see how far we can get. If you enjoyed this video, give it a thumbs up. Feel free to subscribe to the channel and leave me a comment. I would like to know what you think. If you've got input on how all of this should work, feel free to throw that down in the comments. I am absolutely interested in technical conversations. Remember that if you are a supporter over on Patreon, you do get access to the Discourse forums, and we have some ongoing discussions about this. And as I get into the software development, I'll be updating that more frequently, and I'm sure there will be some interesting conversations there. Thank you for watching.